Okay, we're back to continue with the next section. This is chapter 14 in the textbook, over what are called ideals and factorings. I think I said before that this is going to be very analogous to factor groups and normal subgroups from group theory. So let's first define what is an ideal. So let R be a ring. An ideal of R is a subring A with the property for any little a in capital A and for any little r in capital R. If I multiply the two, A times R, that's going to be an element of the ideal A. And because, again, multiplication in a ring is not always commutative. To be an ideal, it has to be both ways. So if I take an element from the ideal and I take an element from the bigger ring that this ideal is inside of, if I take an element from, so let's draw a diagram here. So we got our subset A, and I take an element from A, and I've got my bigger set R. I take an element from that bigger set. If I multiply these two elements, their product is always inside of the ideal. It doesn't matter which way I multiply. They might give me different answers, but both of the answers, both of the products will live inside of the ideal A. Okay, so multiplying by, in an ideal, if I take something from the ideal, I multiply by anything, no matter where that other thing comes from, I always land back inside of the subset. Okay, so before we do examples, let me go ahead and tell you the test for ideals. So this is the ideal test. So let A be a non-empty subset of a ring R. Then A is an ideal if and only if we have two things that we have to check. Okay, so going back to the definition, an ideal has to be a subring. To check something's a subring, we would have to check two things. It's closed under a depending how we number things. The subring test, I believe we covered. To check something was a subring, the faster way was we checked that it's closed under subtraction and it's closed under multiplication. So it has to be a subring, so it has to satisfy both of those things. Excuse me. So for any A and B in A, it needs to be closed under subtraction, so A minus B needs to be an element of A. Now it also has to be closed under multiplication, so A times B would have to be an element of A, but it also has to satisfy the extra ideal condition about multiplying by things outside of A. So that takes precedence. That's a stronger condition. So for any A in capital A, and for any R in capital R is in capital R. Let me rewrite my R. if I take two elements, one of which is in A, then the product, A times R is in A, and R times little a is in capital A. Okay, so the subring test from a couple sections ago, the subring test for the multiplication part requires that both the elements are in the subset. So A and B would be in A, and then their product, A times B, would need to be in A. But to be an ideal, it's stronger. It's a stronger condition. If one of the elements is assumed to be in A, and the other element can be anything, their product still has to be in A. Both their products, AR and RA. Okay, so let's look at some examples. As we go, some of them will apply this test to just to verify. So examples of ideals. Let me start with the simplest examples first. If I just take the 0 element that set by itself of just that one element, that is an ideal. It does satisfy the definition. That's called the trivial ideal. So it's closed under subtraction because 0 minus 0 is 0. It's closed under multiplication because if I take 0 and anything else that's not in this set, multiplying by 0 gives me 0. So for any little r times 0 equals 0. That is an element of this set. So multiplying by that, you land back in the same set. Okay, so that's one example. The other simple example is the ring itself is an ideal of itself. So R is an ideal of R. Because, I mean, it's a ring, so it's closed under subtraction because it's closed under its operations. And it satisfies the ideal condition because if you take something from inside of it and something else, well, the second element also has to be an element of R. So if you take two elements of R and you multiply them, you get something in R. So it's an ideal. It's also kind of we want to be careful with the word trivial. It's another example that's always there. So we say, I don't know what we call that one specifically, but we say an ideal is proper. So an ideal A if A is an ideal of the ring R, but it's not equal to R. So R is a non-proper ideal of itself. Any other ideal is proper, including the trivial ideal. That's a proper ideal. All right, so let's do some non-trivial proper ideal examples. Maybe the simplest, or the one that we're most familiar with, would be even integers. So 2z, that's the set of even integers. This is an ideal of the integers. Okay, so let's just run through the ideal test for this easy example. So it's closed under subtraction. If you take two even integers, so, all right, so I delete my first attempt at saying this. Let's show this is closed under subtraction. So let A and B be elements of 2z. So what that means is then a is equal to 2 times m for some m, and b is equal to 2 times n for some n. If I look at a minus b, that's 2m minus 2n. That's the same thing as 2 times m minus n. So that's an element of 2z. So an even number minus an even number is an even number. So that's closed under subtraction. Now our second part of the test is closed under multiplication, in a sense. We have to be more specific. Closed under multiplication with z. So we take one element of 2z. A is an element of 2z, so we can say a equals 2m for some m. And we take a second element, we'll call it r, and it's just an integer. So we can't say that r is is even. We just know it's an integer. But if I multiply what is a times r, that's 2m times r, that's 2mr. So that's 2 times some integer. That's an element of 2z. And by the way, since we're dealing with a commutative ring in this example, AR times RA are the same thing because multiplication is commutative. So I just have to check one of them. I don't have to write out both of them each time since it's a commutative ring. So A times R lands back in the subset, so that's the second part of my ideal test. Therefore, 2z is an ideal. All right, let's do an abstract example of a way we can construct ideals. And really this is an example of this next construction I'm going to define. But this will allow us to make up a lot more examples quickly. All right, so let R be a commutative ring with unity. So I'm abbreviating, but commutative ring with unity. And I guess I'll use A. Let A be a fixed element. Yes, just let A belong to R be fixed. So we pick our favorite element, and now we're going to generate an ideal based off of that one element. So we use this angled bracket notation that we used to use in subgroups. So the subgroup generated by A was with this notation, but now we're in a ring, so this angle bracket stuff is about ideals. This is the, I could say ideal, but it's the principal ideal generated by A. So principal is extra bit of description there. It's really the ideal generated by A. And since it's generated by a single element, that's what the word principal means. I'll show you an example that's not principal later. All right, so this is defined to be the set of every element of R which can be written with A as a factor. So it's things of the form. So it's commutative, so it doesn't matter how I write this, but let's say R times A, such that R is an element of capital R. So just for illustration, in Z, the principal ideal generated by 2 is the set of integers that have 2 as a factor. So this would be exactly the even integers that we were calling this before, 2 times the integers. Right? So that's just a example. This is a generalization of this even integer business to other commutative rings. Okay, so let's prove this is an ideal. Let me give myself some more space. I'll rewrite the definition. Okay, so I want to prove this is an ideal. So first, subtraction. So I need to take 2 elements of this thing. Unfortunately, I can't use A for one of them because I'm using A as my fixed element that's generating this thing. So let's use B and C. Let B and C be elements of this. Since they're elements of this, that means they can be written in this form for specific choices of R. So then B can be written as, we'll call it R1A, and C can be written as R2A for some R1 and R2 in capital R. So therefore, if I check subtraction, B minus C, that's R1A minus R2A. These have A in common, so by the distributive property of rings, we can pull the A out, and we have R1 minus R2 times A. And the point is, this is something times little a. So by definition, that's an element of this ideal, of this set. It's something times a, that meets this definition. Okay, so that's the first half of our ideal test. Now let's, again, we'll go with the same B here. So B is an element of this ideal. B is R1A. Now I don't need C. What I need for my second element for the multiplication part is some other element of the big ring. So now let's let R2 be an element of R. Then BR2 is, all right, this is a commutative ring. R was commutative. I should remind you of that. It was a commutative ring with unity. That reminds me, I missed one thing I need to go back and say. But, so since it's commutative, BR2 is the same thing as R1AR2. But it's commutative, so multiplication can be rearranged however I want. So I can put these R's together like this. Now it's something times A. So that's an element of the set generated by A. It's some element of R times A. Okay, so I've done the hard part of the ideal test. I skipped the easy part. Let me go back and correct myself. So I'm going to erase. Just like with our subgroup tests from way back, we called them things like the two-step subgroup test or the one-step subgroup test. There was always this extra hidden step, however, and that was that it has to be a non-empty set. So how do I know this is non-empty? Y is how do we know this is non-empty? I have to come up with something of this form. Well, as soon as I can produce a single element of this form that can be written in this form, that tells me there's something in this set. So I just have to pick any element of the ring. For example, R or 0 sub R times A. That's something from R times A. It happens to be 0. That's in this set. Okay, so 0 is in this set, definitely. There's other stuff. If A is non-zero, then there's other stuff as well. But what was throwing me off while I was thinking of this, the fact that this is a unity ring, a ring with unity. What if I pick 1 for my R? So this is extra. We answered the question why it's non-empty. But since R has a unity element, 1 sub R, I can use that as my little r. 1 times A equals A, and so that tells us that A is an element of this ideal. So I mentioned this because one way of saying that, one way of describing what this ideal is, it's the ideal generated by A, and what we want that to mean is it's the smallest ideal that contains little a. So of all the ideals that contain A, this is the smallest one. If something is an ideal and contains A, it has to contain this entire set. Okay, but that part's only true if we are doing this inside of a ring with unity. Because if I don't have a unity element, nothing tells me that I can find an element that... Nothing tells me I can factor A as something times A. I have to have a unity to be able to do to guarantee that I can do that. All right. Let's do another concrete example with this construction. All right, so now in the polynomial ring ZX, come here. All right, she's just gonna stand there and heckle me. In the polynomial ring ZX, we've got the polynomial x, so the polynomial that's just x, that's 1 times x plus 0, that's a polynomial. Let's look at the ideal generated by that polynomial. So this is an element of zx, so then it generates an ideal. By our definition, it's the set of everything in our ring that can be written as some element times this generating element. So what that means is, I'm going to alter this, but just by the definition, it's Rx, where R is an element of our bigger ring, Zx. Now let me be a little bit more deliberate with how I choose my notation. What is an element of Zx? It's a polynomial. So let's call it P of x. So what this is the set of all polynomials that have x as a factor. Let me write that in. Set of all polynomials with integer coefficients because of the z, with x as a factor. Okay, so for example, just to write a couple examples. If x is a factor, and I've got like 3x squared minus x plus 5 times x, then x is a factor, but if it wasn't factored, what that would tell me is I don't have a constant term, right? So 3x cubed minus x squared plus 5x. I have a 0 constant term. Okay, so another way I could say it is these are polynomials in my polynomial ring that have 0 as a root. So if I can factor out an x, that means if I plug in 0 for x, this whole thing becomes 0. So another way I could describe this, a better way to describe this specific example would be those polynomials f of x in zx such that f of 0 is 0. So 0 is a root. Because if f of 0 is 0, that means every term has an x, so I can factor out an x from the whole thing. Right? Similarly, let's do another one with the same stuff here. Rather than use x as my generating element, let's do a linear polynomial like x minus 2. So again, by the definition of principal ideal generated by x minus 2, this would be things of the form x minus 2 times some other element p of x in our polynomial ring. So these are polynomials that I can factor x minus 2 out of. That factor with x minus 2 as one of the factors. But more concisely, if my polynomial can be factored like this, that tells me that if x equals 2, I would get 0 out of it. So this would be all the polynomials in zx. So all the f of x polynomials in zx such that f of 2 equals 0. Okay, so let's just pause here and just think about this example from the perspective of the ideal test. Like if I hadn't generated it like this, but I was just defining this as a set with this as my condition, just think to yourself, does it satisfy the requirements of the ideal test? Well, if I have two polynomials that satisfy this condition, then if I subtract them, their difference also satisfies this condition. Like if f and g both satisfy this condition, so they're both integer polynomials, and they both have 2 as a root, then their difference, f minus g of 2, that's going to be f of 2 minus g of 2, which is 0 minus 0, which is 0. So their difference, the difference of these two polynomials also satisfies this condition. Now, for the multiplication condition, my second polynomial g might not be in this set. One of my polynomials is, f of 2 is 0, but if I take a second polynomial, it has to come from the whole polynomial ring. So we don't know what g of 2 would be. But if I look at f times g of 2, that would be f of 2 g of 2. And I don't know what g of 2 is, but I know f of 2 is 0. So the product comes out to be 0. And that tells me that f times g of 2 satisfies this condition, so it lives inside of this ideal also. So we could verify this is an ideal just by using this other definition. All right. Let me do one more abstract construction here. So again, R is a commutative ring with unity. And now, rather than have just one element fixed, I'm going to take a collection of elements. We'll call them A1, A2, etc. up through A sub, I don't know, K. So we have a bunch of elements that we take, and then we are going to generate an ideal from this set. The notation is the angle brackets mean generated by, essentially, but now we have a collection of generators. And so what this is going to be, in the context of a commutative ring with unity, what this is going to be is the smallest ideal that contains all of these elements. So this is the ideal. It's not principal necessarily, because there's more than one generator, but it's the ideal generated by the collection of elements, A1 through AK. Okay, so let's just think about what it needs to be. If it's going to contain each of these elements, so if it's going to contain A1, it has to also contain every multiple of A1. So everything I can get by multiplying by A1. So it has to contain everything of the form R1, A1. I'm going to need more than one R here. But the same is true for A2 and A3, all the way up to AK. So it has to contain all those as well. And then it also has to contain, it has to be a subring, so it has to contain all sums I get from things that are in the ideal. So once I have R1, A1, everything of that form, and I have everything of the form R2, A2, I also have to have everything of the form where I add those two things together. So what this is going to be is the collection of everything I can obtain by multiplying A's by elements of R and adding up those products. So R1, R2, up through RK can be any elements of R. So that's the set of everything that can be written in this form by picking these elements from R. Right? So I'm not going to prove that this is an ideal. It'll be very similar to the proof for the case where there's just one of these A's. It's just more of a pain to write up because of all the subscripts. Okay. So let's look at a couple examples. So in the integers, let's take the ideal generated by two separate integers. So let's say 8 and 12. Okay, so by the definition of this construction, this is the set of everything that I can write as a combination of 8 and 12 using coefficients from Z. So it'd be everything in the form 8m plus 12n, where m and n come from the total ring Z. Now, what is one element that can be written like that? Well, 4 that's equal to 8 times minus 1 plus 12 times 1, for instance. So that fits this form. So that lives inside of this ideal. 4 is an element of this ideal. Once 4 is there, every multiple of 4 is there. So in this example, once I have 4, I get every multiple of 4. So 8 and 12 are both multiples of 4. So therefore, I don't really need to use both 8 and 12 to generate this stuff. All I really need is 4. So in this example, this ideal is actually generated by just 4 because it's the greatest common factor of 8 and 12. So I can always reduce to the greatest common factor and just use that to generate everything in Z. Okay. So if I generate an ideal with if I can generate an ideal with just one element, that's what we mean by principal ideal. So this is a principal ideal. And in Z, we're not going to talk too much about this, but in the integers, any ideal can be generated by one element. You can find one element to generate the whole ideal. So this is a special type of ring called a principal ideal domain. You don't need to know that, but I just wanted to mention it. There's tons of definitions in ring theory. Principal ideal domain is one of them. Not every ring has that property. So let's look at another example where this doesn't work like this. So let's do ZX. Let's take the two elements x and 2. So these are separate polynomials. But they're both integer polynomials. So by the definition, this would be everything that can be written as a polynomial times x plus a polynomial times 2. So this would be like p of x plus q of x times 2. So 2q of x. I want to do 2q of x. I guess the way I wrote the last one was like x times p of x plus 2q of x, where p and q are elements of zx. Okay, so let me just look at it specific. Let me make a choice on a p of x and q of x. So, for example, x times 5x plus 7 plus 2 times a q of x, let's say x squared plus x plus 3. So this fits this form. Now if I simplify it though, and combine like terms, I get 7x squared plus 9x plus 6. And so this is also of this form. So let's see why. These first two terms, 7x squared plus 9x, I can factor an x from that. So this would be x times 7x plus 9. The 6, I can factor a 2 from that and get 2 times 3. And so my point with this example is, if I want to understand what this ideal looks like, it's really just about the constant term. So if I have a polynomial that can be written like this, xp of x, because I'm multiplying by x, this part here will not have a constant term. It'll have a 0 constant term. Whatever constant term I get from 2q of x is going to be a multiple of 2 because I'm multiplying by 2 there. So in words, as a set, this is the set of all integer polynomials with even constant term. Okay, so if you want to check for this specific example, check that it's an ideal. Think of it in terms of this definition here. If I take two integer polynomials with even constant term and I subtract them, that new polynomial will still have an even constant term because I'll just be subtracting the constant terms. Even minus even, still even. If I take one like this, one polynomial that satisfies this, like x squared plus 3x plus 6, and I take another polynomial that doesn't satisfy this, so like x plus 7, when I multiply them, the new constant term is going to be the product of these two constant terms. Since one of them is already even, that product will be an even constant term. So this definition, this set that I've described in words here, satisfies the ideal test. Now it happens that we can generate it this way, with x and with 2. But the other point I want to make about this example is I can't generate this with just one element. Okay, like if I dropped x and just generated the ideal with 2, that would force every coefficient to be even. It'd be the set of all polynomials with even coefficients. If I drop 2, then that's forcing my constant term to be 0. And that's not the same thing. And I can't really find some other polynomial that'll generate this set. Because kind of like we saw with our earlier example, if I pick a polynomial like this, what that does is it tells me what my polynomials, it tells me what a root of the polynomial has to be. So if it's generated by x plus 4, that would be the set of polynomials that are have negative 4 as a root. Okay, so this, let's just leave it like this. This ideal cannot be generated by a single polynomial. So this is not a principal ideal. Okay. So no, well, we're not done with this section yet. But over the basic concept of ideals, you want to be able to apply the ideal test. So if I describe a set to you, you should be able to prove or disprove that it's an ideal. Yeah, so the next topic, we'll stop the video here, but the next topic will be defining factorings, which are defined using ideals.